All right, so hi everyone, I'm Phil. If you don't know me, I think I know almost everyone in here, but if you don't know me, today I'm going to be talking about clique percolation, which is sort of a neat little like clustering algorithm we can use to analyze graphs. It involves some combinatorics, some random graphs, so it'll be interesting. But first, actually, here's the outline. So we're going to talk about something called percolation first, which is I don't know. It's a bit of a side tangent, but there's some cool diagrams I have, and it's related to what we're going to talk about later. So we'll start with that. Talk about random graphs and how they have phase transitions, and then talk about cliques and what the clique percolation algorithm is. So percolation. You guys have probably heard this word, but maybe not in a math context. Percolating water, maybe. And so there's this problem when we talk about like physics and talk about percolation theory, which is sort of like assume that you pour some liquid on top of some porous material. Will the liquid be able to make its way from hole to hole and reach the bottom? Right. So this involves some sort of material which is like mostly solid but has some gaps in it. Right. And so you can model this by thinking of like some sort of three-dimensional vertex graph. And then they have sort of edges connected to their neighbors, and they might be either open or closed. And we're going to say that this is randomized with some sort of probability. And then the question is sort of, for a given P, what is the probability that an open path exists from the top to the bottom, right? So here we have some pictures taken from Wikipedia. So these are like coloring the sort of different gap clusters that exist in the material. So top left is P equals 0.3, which is like the most closed, right? And so all the gaps are kind of disconnected. And as we can see, as you go from left to right and then down a row, left to right, like the gaps start joining into larger and larger clusters as we increase the probability. And at the bottom, we're getting like very, very close to 0.5. So we have 0.486, 4905, 493. And as we can see here, it kind of just like magically starts to take over the whole thing at exactly 0.5. And as it turns out, that's a result that you can prove. I'm not going to do it here because it's a long proof and I don't really get it. But a similar idea extends to graphs. So that's what we're going to look at next. The topic that we're going to cover now is called random graphs. I don't know if you guys have seen these or not. We talked maybe a little bit about it in 473. Actually, I'm not sure. But the idea is basically that it's similar to the graph theory that we do in 225 with like edges and nodes. But we're saying instead of defining the graph in a certain way, what we're going to do is define it probabilistically. So the most popular model for random graphs, because it's sort of the most intuitive and simple to understand, is the Erdos-Renyi model or ER graph. Basically, what you do for these graphs is you add n nodes, and then you add edges with probability p. There's also an alternate form with n and m, where you add n nodes and then pick uniformly from all configurations of m edges. Sorry. And so with these kinds of graphs, like you're sort of like running an RNG to like make a new graph. And so the structure is different every time, but there are some patterns in it. For example, if you set P to 0.5, right? That means basically you're taking all the nodes and you're connecting all of the edges and you're saying like, oh, 50% this is connected, 50% this is closed. So you can think of that as actually like sampling from all graphs with equal probability that are possible, right? Because you're picking open or closed over all the edges. So that produces a nice like binomial theorem sort of thing. But we're going to look at p-values that are smaller than 0.5 for this. So as you might be able to tell, like this is pretty similar to the percolation problem, like connections, probability. When we look at the NP model, each edge has a fixed probability of being present or absent independently of the other edges, right? We're assuming full independence of edges and nodes, which might be a little bit like unhelpful for a model. You know, most graphs have some sort of clustering or what's called correlation. And there are actually other random graph models that do incorporate that, but they're a bit more complicated to work with. And then once you incorporate that, then it becomes less about percolation, and we're interested in percolation for this problem, so we're going to stick with this. Before we talked about the threshold of 0.5, and it was sort of a magic number, right? Well, a random graph, if we think about like, instead of thinking about like path from top to bottom within the square lattice, now we're talking about a random graph, and we're seeing like, can we connect the majority of the graph together to one component? Answer is yes, and the magic p-value which does that is determinable. Basically, if you go into the book which I cited for this, it was Erdos wrote it. He basically goes through like 12 different theorems. He's like, if p is less than like some very small number, all the nodes are disconnected. And then if it's a little bit bigger, then you can say there's a path, and then there are trees, and then there's like multiple components, but they never reach a certain size, and then they all sort of connect. So the sort of structure of the graph, depending on like the value of p you set, is like very easy to predict, even though it's completely random, just because of, you know, large numbers, randomness sort of evens out. And I'm not going to be talking about how to prove that stuff in this presentation, because it's mostly like, you know, turn off bound sort of error sort of proving, which is tedious and would take a while to go through and not really relevant to combinatorics, but it is cool nonetheless. I would look at the citations that for this presentation if you're interested in that. And so we have some pictures. Basically, I took this website, you generate random graphs. These have 50 vertices each, and 1 over n, which is the like sort of magic number. In this case, would be 0.02. So here I took 75% of 0.02, so 0.15. You can see that in each of the random graphs, there are some connected components, but they're sort of strewn about. A lot of the vertices aren't connected. And then if you increase 0.015 to 0.025, like the structure completely changes. These components are almost all connected. Like, so the majority of the vertices are connected in one component. So it looks completely different than it did before, which is cool to look at. And so basically what we've done is we've created a giant connected component made up of nodes connected to each other. But then sort of a question might emerge, which is sort of like, okay, we've done vertices connect to other vertices, but can we sort of extend this idea and generalize it a bit? So instead of like connection to connection, why don't we think about like clusters where we connect click to clicks instead of nodes to nodes? And it turns out that this is exactly the idea behind the algorithm, which we're going to go over to find clusters and graphs. You look at clicks, and you look at clicks overlapping with other clicks to find this connected components, but not connected in this terms of like connected on a graph, but in terms of like click connected on a graph. So what does that look like? Here's a graph. We've got some points. We're going to be looking at this a bit while we review what a click is. So if you guys have not learned it, a clique is a fully connected set of nodes, which means that every pair of its vertices is connected by a link in the graph. So for example, we look here, we've got these triangles, right? A triangle is made up of 3 points, and each point is connected to each other point, right? So 3, 4, and 5, 4, 5, and 6, 1, 2, and 3, they're all 3 clicks. So k click means a click of k nodes. So any triangle is a 3 click. If you look at 3, 4, 5, and 6, those are all connected to each other. So that's a 4 click, so on and so forth. And we can also identify like adjacency. So if we take any 2 k clicks, we can say that they're adjacent if and only if they share k minus 1 nodes. And so you can look at like 3, 4, and 5 is adjacent to 4, 5, and 6 because they're both 3 clicks. and they share 2 out of the 3 nodes. So you've got these overlapping triangles, but it generalizes to larger stuff too. And so when we talk about like a clique percolation method community, that's sort of what this algorithm is looking for. It's looking for these kinds of clusters that are defined as the maximal union of K cliques that can be reached from each other through a series of adjacent K cliques. And so you're sort of connecting all of the adjacent cliques of the same size together. How do we intuit what this means? Start with a clique in your mind, and you can do this thing where you like roll it over in your mind. So like if you take 1, 2, and 7, 1, 2, and 7, you can be like, okay, get rid of 7, put 3. That still works. So these are adjacent and they form a sort of clique community. An idea I came up with was like a group chat of Theseus, where you take someone out and put someone new in. And as long as you keep doing that, and they're all cliques, then it's a valid community. And so on this graph, there are 2 3-clique communities, which are the red and green. So if you ran the CPM algorithm on it, you get that. They kind of make sense, right? They're connected to each other. It sort of intuitively looks like what you would think are the clusters on the graph. Any questions about that background so far? Making sense? Cool. All right. Actually, let me go back 1 slide quickly. One cool thing about this algorithm, which makes it useful, is that you can have vertices that are in multiple cliques. So in this case, multiple clique clusters. So 3 is in both the red cluster and the green cluster. A lot of clustering algorithms will like put stuff in exactly 1 cluster. But you can see based on the structure of this graph, like 3 is pretty clearly in both clusters. And so it will place 3 into both the red and green because they're part of both. Cool. So clique percolation algorithm, what is this actually doing? How does this actually work? So the idea behind this algorithm is we want to understand the structure of a graph, the communities within it. There are some different use cases of this. For example, I think the most obvious one is social media. You connect like different users in a network. You have a network, you want to find out what the communities are. There are also other applications of this. For example, in biology, you might have like a bunch of proteins and you know that they all interact with each other, but you don't know exactly how to understand the data. So you can make sense of it this way. Any sort of like networked thing. And so the good things about our algorithm are that the things that we get from it, the clusters, are pretty intuitive. They're also deterministic. So every time you run the algorithm, you'll get the same thing. A lot of other clustering algorithms are kind of random in some sense. You'll get a cluster that makes sense, but then you run the algorithm again, you get a completely different clustering. There's exactly 1 solution for this algorithm. So you will always get that. You will also get overlapping communities and nodes in multiple communities, which is good. And if you adjust K, you can adjust the sort of density requirement that you need for your clusters. And so that's pretty neat as well. Okay. So there are 2 things that we need to think about before we start this algorithm. One of them is, well, okay, we're putting cliques together into clique clusters. How do we find cliques? That's sort of its own bag of worms. It is an NP-hard problem to either find all the maximal cliques or find all the K cliques in a graph. So it's not the kind of thing that we can sit here and like come up with like a precise solution on the board, which we can prove is best. You know, it's something where we just have ideas and we come up with them and we try to make them faster. For example, one of the papers I read for this presentation came up with a new approach which parallelizes it, makes it a lot faster to compute. And they did that by making it like less efficient but parallelizable as opposed to what was used before. So sometimes optimization takes weird steps. So for our algorithm, we need a data structure, right, to store these. And as it turns out, the most natural one to use is disjoint sets, which is the kind of thing like you've never heard about before coming to university, and then you learn about them briefly. Union find or disjoint sets are super cool, and I would highly recommend you look up how they work if you don't understand them very well. I'm not going to go into a super deep explanation, but basically, as the name suggests, it's a structure for storing sets that are disjoint from each other. And so they typically have these three operations: make a new set, find, which means that you return the root of a tree, sort of like one node that represents the set as a whole. So put in any vector or node, which is supposed to be part of the disjoint set data structure, and you get one node which is associated with the entire set it's in. And then you can do union, which means that you have two sets in the data structure and you sort of combine them into one set so that they all refer to the same thing. Super cool structure. So this is basically the algorithm. It's simple. There isn't a ton to it. In its basic form, there are optimizations that you can do. But basically, start with a union find data structure in a dictionary, and then having computed all the clicks using whatever technique you use, which there are pros and cons to. I can talk more about that after. You go through all of the k-size clicks you found, and then what you do is you sort of combinatorically, find all of the k-1 size clicks within that k-size click. And if it's already in your dictionary, then that means that you've sort of found that k-1 click already, which means it's already part of some sort of disjoint set. So you just find whichever, like, you basically get the set that this is in. Otherwise, you make a new set because the subset you're working with is new. It hasn't been seen before, and you put it inside the dictionary. And then what you do with S, which is the set, which is representing all of the k-1 disjoint sets your k-click cluster is made up of, you sort of join them and you go through all of the subset clicks. You join all of the disjoint sets they're a part of, and then you join all of those together. So yeah, it's fairly simple. The reason you do k-1 is because these k-clicks overlap, and so if they overlap, that means they have a k-1 click in common. So you find the intersections by finding the k-1 clicks that are already in your dictionary. And yeah, it's kind of slow. It's not a great algorithm, but it works. Do you guys have questions about how that worked so far? Yes.
Do you have to find a k-1 click every time, or is every k-1 click that's a subset of the k click automatically, like a fully connected graph and everything?
So if you have, in general, if you have a click like go all the way here, right? If you have, like, let's say k is 4 and we're talking about 3, 4, 5, 6, like the subset clicks are themselves clicks. That's kind of how they work. Like if it's fully connected, then the subsets of them will also be fully connected.
Right. So there's no extra computation in finding the clicks within another click. It's just automatically assumed that.
Yes, that's true. So the reason the algorithm is slow and memory intensive is the bigger one I was going to go into later, is because of two things. One is computing using the first place, which I kind of glossed over and said that you use the best tool you have available. Basically, the papers that I read talked that there were two approaches to this. One is that you can find all of the maximal clicks in a graph, and they were saying that's like intuitively what you should do. But then a few other papers said, actually, if you just ignored that intuition and just find all of the k-size clicks on real data, that works. pretty well. And so the parallel algorithm finds all the K clicks without thinking about the larger than K clicks. And so it finds all of those. So that's slow. And then memory intensive is that this dictionary becomes enormous because you store every K-1 click that's in the graph essentially. And so one thing which might not be obvious if you haven't thought about this problem is that if you have a graph, there are more clicks in the graph than there are like nodes in the graph. I mean, like, think about it for 10 seconds. Like, of course there are. Like, think of a deck of cards, right? And think of these clicks as being like any 5-card hand, right? There are way more 5-card hands than there are cards in the deck, right? Which means that you're storing every one of these combinations. It's really memory intensive. But that's one of the downsides to this algorithm. But it does work. Yeah, okay. Any other questions before I go over the memory optimization? Cool. So, oh yeah, let's talk about percolation thresholds first. So we were talking about 1/n being the threshold for the random graph going from disconnected to almost fully, not fully connected, but connected component. Right. And so the question is, can we figure out what P would be for our clusters? Like, how likely do the edges have to exist in order for us to have one giant cluster instead of one connected component? Obviously, this should work with the connected component case, because if you think about it, like one pair of nodes is a 2-click. It's like 2 points connected to each other. So like K = 2 is the same as the normal graph. But then if we do K greater than 2, how is P going to change? And so one of the papers basically walks you through the intuition. If you think about it, the thing that's happening at the threshold is that at any point within like your rolling over process where you're going from adjacent click to adjacent click, at the threshold, there should be an expectation like a 1 adjacent click at each click to continue to build it, right? Because if it's less than 1, then you would expect early termination. And if it's greater than 1, then you would expect like the graph to probably fully connect. And so =1 is the sort of minimum case where you can build a cluster. And so you can create this equation, which is basically, if you're at a click, there are K-1 ways to take a K-1 click, which is the intersecting subset with the adjacent click. So K-1 ways to make an adjacent click. And then which node do you pick? Well, there are n-k, there might be n-k plus 1, but anyway, n-k minus 1 times the p-value that you have to the power of K-1 equals 1, right? 1 is our in expectation. And if your n is large enough, because you're working with a big graph, that basically becomes n times K-1, p to the K-1 equals 1. And that gives you this equation. So for example, if you plug in 2, you get 1 over n times 1 to the 1, so it's 1 over n. But if you plug in bigger values of k, it becomes a smaller number, no, a bigger number, because you're taking denominator is bigger, but then you're raising it to a sort of square root power. Yeah, so it ends up bigger. Optimizations. So the CPM algorithm is prohibitively expensive in memory in particular, because we store a large number of K-1 clicks. And so what the paper suggests is, let's not use K-1 clicks, let's use Z clicks. So Z is we just pick an arbitrary number which is smaller than K-1. And what we do is we change our algorithm to do non-disjoint sets of smaller than K-1 clicks instead of disjoint sets of K-1 clicks. It sounds a little bit weird, but it does make sense because if you think about binomial theorem, right? If we go back to cards, right? Choosing a number of cards from a deck. The number of cards that you choose that like maximize the number of combinations is n over 2, right? You might recognize this. It's like if you pick only one card or you pick 51 cards, that's the same. If you pick 2 or 50, it's the same. And so it sort of increases and maximizes in the middle, right? And so if you assume that k is way smaller than the number of edges, that means it should be below that half point, right? Which means that if you're storing z clicks instead of k clicks, if you're reducing the size of the click, that means that there are less of that click, all the way down to 2. And so I think in their paper, they actually use just size 2 or size 3, which is basically just storing like edges or storing maybe like triangles. And it turns out that you can do the algorithm like this. It's not identical because of the non-disjointness. It only leads to an approximation of the communities, but in practice, it was like 98 to 99% similar. It's a slower algorithm because of the non-disjointness, but it also uses much less memory. So that's the trade-off you do. Any questions on that? Cool. That's all I had. There was a lot of reading that went into this, but most of it didn't end up in the presentation. So you can ask me about it if there's something you found interesting. But yeah, good stuff. Look at this stuff. These are cool papers, and this book is the one with the proofs. So look at that. Yes.
So these threshold probabilities talked about.
Yeah.
These are threshold probabilities for when a graph almost surely has segment.
It's I think I took it out of the presentation, but the statement is like almost surely that the graph has one giant connected component, which is I think greater than half the nodes. I don't know. It's like very well defined for random graphs. It's very precise. But there's this idea, I can't remember what the theorem is called, but it's like 0-1 theorem principle. I cannot remember. I don't know if it's ringing a bell with you too. But it's sort of like there's either something doesn't happen or it almost rarely happens, and then there's a very fast transition. And so this is sort of the probability of which that transition is happening.
I see. Okay.
Yes. Any other questions? Cool. Well, thanks for coming. Can I check Zoom quickly? No, we're good there. Yeah. Good stuff.
Thank you.
Yeah.
Sorry. 30 minutes. Like 4.